I'm talking to the people in the back. Yeah. Can you hear me? Yeah? Okay. Well, okay, thanks, Edward. Thanks, Edward, for the introduction. So I'm going to talk today around this this autograder that we designed originally for the MOOC version of this class that ran from May to June last year, and then that you have been using during the previous labs. Okay, so the title of this, I titled this Autograding a CPS lab, so it's a generic title using signal temporal logic. So essentially I'm going to introduce... Yeah, it doesn't look so. Okay. Otherwise, we can... No. Yeah. So I guess we can use this the other one. Oh, this is working now. Okay. So does the microphone works now? I'm still talking to the people at the back. It's what? It doesn't work? Oh. Yeah, okay, it has to be very close, actually. I thought this thing wasn't... Okay. Okay, I'm going to talk like this. I don't like it, but anyway. Okay, so...
I would go ahead and put it on your lapel and just try to...
Yeah. Okay, I'm going to go ahead and talk like this and interrupt me if you cannot hear me. All right? Okay, so I'm going to start trying to make a connection with the previous lecture by Alberto. What does it mean to grade a CPS model design, right? So, I mean, the purpose of grading, there are two purposes. So the first purpose is to, okay, does the design meet the assignment of the lab? Like this. So you have an assignment, you should build a design that does this or that. And so does it mean this assignment? And of course, students are not perfect, and they make mistakes, and I mean, it's our job, the job of instructor, to help them understanding what went wrong. So grading is not only verifying that design worked or the problem was solved, but also about even if it works, I mean, if it's imperfect, if it doesn't work, or even if it works, finding the imperfection in this design and trying to give feedback to the students. So if you have an imperfect design, then provide some explanation of what went wrong. Right? So last week, Alberto talked about a technique to automatically verify that the design satisfies our requirements. So that can be used for the first purpose. Like there's a design meet the assignment. It's model checking. And model checking comes with a nice feature, which is that If the design does not meet the requirement, then you get a counterexample. So this can be taken as an explanation or as a hint. Right? Now, okay, so model checking is about does the model satisfy some specification? And what we are going to present it is a model, in the case where a model is a finite state machine, and specification are LTL formulas. In the case of a cyber sim, of the iRobot Create, what we have actually is some hybrid system. Right? It's not really directly in a finite state machine. Right? And the specification I'm going to talk about are an extension of LTL, which is called signal temporal logic, which is more adapted to this case of hybrid systems. Okay. So one problem is that model checking STL is intractable for complex CPS, and that's a case of CyberSim. This is a complex cyber physical system. This is a complex system, and so in that case we resort to what we call lightweight verification, or sometimes runtime monitoring, which is a more tractable approach, which results in simulation and monitoring. That is, the model produces some trace, and we have some monitor that's going to say, okay, this trace is true or false. And if we really want to verify, model check this model, we would do this for every possible trace of the model. Okay? So think of it as an incomplete depth first search for model checking. Like you're doing simulations, and if you're doing an infinite number of simulations, then you're going to model check your system. But if you're not, so the nice thing about it is that if you cannot do an infinite number of simulations, obviously, you already have a result over the finite number of simulations that you have. Okay, so you already know for the finite number of simulations that you did if the property was satisfied or not. So you have information, and it's particularly useful. So you can still easily find counterexample in that case, because if any one of the simulation did not satisfy the specification, then you have your counterexample. But usually, you cannot prove that the system is correct, because you cannot do this infinite number of simulations. There's too many states. There are too many of them. Okay, so if you come back to LTL. What does it mean to monitor an LTL formula? So it means that you have a trace. So let's say you have a trace, which is some AA, AAA, all right? And as you know, the simplest LTL formula are predicates like A or B. So monitoring this is just finding the true value of this predicate on this sequence. So A is true, 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 false there, and true, etc. Now, how do you monitor next B? Well, as you know, the formula next B is true if B is true at the first time point of the sequence, right? So, and the next says the event after. So if you look at the first event and the event after, you look at the validity of B, and you get the satisfaction of next B. Okay, so you can monitor. And you can do this for subsequent times if you want. Okay, so now what's the validity of always A? Well, you look at the sequence, and always A says that for every event, A should be true. So you look at, so it's true, 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 and then at some point it's false. So this false just provides you a counterexample for always A. Okay, so my formula is false. Now eventually B, same thing, you look in the future, and if you see a true, then your formula is satisfied. So etc. And same thing for until B. Okay, so yeah, so this is I mean briefly how you would monitor an LTL formula over a discrete sequence of events. So please interrupt me if you have any question at any point. Yeah.
Why is the
about these question marks there?
The third one, which one?
Yeah. So, okay, so if you look at always A here, and if you evaluate this on this suffix of this formula, well, because you are in a monitoring situation, it might be you don't have all information. You have a finite observation of your system, right? So it says, okay, it says it should always be true, but you don't know because you don't know the future. So all you can maybe assume that this is an assumption. Okay, maybe it's true because all I know is so far, all I've seen is true so far, but actually you cannot tell.
But so in that case, if you can't like look that far into the future, then in the very beginning when you only saw A's, and like how are you able to look in the future to see that there were B's?
Sorry.
So for always A, you have false in the very beginning because sometimes A is false.
Yeah.
But like you just said that there's like this limit, like there's this horizon where you can't see into the future. So how come you can see into the future in that case but not after?
Well, and all truth values that I put here without the question mark are definite truth values. I mean, it does not depend. It only depends on this the prefix of this sequence, and does not depend whatever happens after. So it's done. So, and I mean, what this illustrates is that in the monitoring case, because you have finite traces, especially when you have like eventually, well, you have cases when you cannot decide. Right? Because some formula you can only decide them on infinite. Yeah.
I'm not sure I understand. For every formula that has G or F, or even U, we can never know for an infinite series. We don't have the infinite series, right?
Yeah, we don't have the infinite series.
So you only decide on what you have on infinite series?
Yes, you do what you can.
And
This I did what I can, so I can say here, I can say that this is true. Because A is true and then B is true. But I cannot say that this is true because I don't know whether there will be a B. Yeah.
So just a question on the U at the bottom there. Isn't it possible that the B's could also be true because A just isn't true for any of them, and it just immediately goes to B?
Okay, so here I put the truth value of A and B on the trace.
Right. So I'm just saying on the final row.
Yeah.
Why is that not true right there?
That's
A
true
is
because
true until B, but it just isn't true.
here A is true. A is true until B is true. Right? Here A should be true at the first.
Doesn't A not have to? Can A just not be true and then just go straight to B? A has to be true at least once.
Well, in this semantics here, no. A has to be true at the first. Okay. So after this first small reminder on LTL, I'm going to switch to the rest of the talk. I'm going to talk about STL, so signal temporal logic, and then I will switch to CPS graders, so the auto grading system that you use in CyberSim. All right, so STL is an extension of LTL with real-time and real-value constraints. So to give you a first supporting example, running example if you wish. So the classic property in LTL, request grant property in LTL is like always when you have a request, then eventually you get a grant. Okay. So in this LTL formula, we have Boolean predicate. R is true or false. Grant is true or false. And we have discrete time. That is, we observe sequence like discrete events. Okay. The first extension of this is with real time, where now we say always when we have a request, then eventually in 0.5 seconds we get the grant. So here we still have Boolean predicates, R is true or false, J is true or false, and we have the requirement that G happens in 0.5 seconds, and it could be like any real time value. And STR has a layer on top of this where in R for the predicates, you can specify, you can talk about the signal values themselves. So x and y are signals. Now we have predicates that are over signals with real values, and we have real time. Okay. So, and if I detail a little bit more about the syntax, so we assume that we have signals which are functions from R to R, so that is the dance time signal. And for example, in our case, we have position, x, y, z, orientation, sensor values. These are all functions of time, and that goes into the real. Then we denote by x of tau the value of signal x at the time tau. Then atomic predicates are inequalities over signal values at a symbolic time t. So, okay, so x of t greater than 0.5, z of t smaller than 4. LWS is, in our case, is left wheel speed and right wheel speed greater than 100. And when I say symbolic time t, I mean that when I will evaluate this formula, I'm going to replace this t by a concrete value. This becomes clear.
In the previous slide.
Yes.
So what's the main difference between FTL and STL? Like R could have been xt greater than 0, right? So it's also a Boolean kind of function, right?
Yeah. I mean, STL, in the syntax of STL, we explicitly use values of the signals.
So just that it's explicit, but it's still a Boolean function.
Yeah, it's still a Boolean function. Yeah, it still translates to MTL once you get the Boolean values of this. Okay, so temporal operator we have future globally and until as for LTL, except that now they're equipped with a time interval. So for example, future in 0.2 seconds, x of t greater than 0.5, always 0.40, y of t smaller than 0.3, phi until in 1, 2.5, psi, etc. Yeah.
Can you please explain the semantics of the U formula? What if psi doesn't appear at all?
So the semantics of the until formula there will be, it will be phi is true until sometime between 1 and 2.5, psi is true.
So psi has to...
Psi, in this semantics, psi has to be true.
Between 1 and 2.5?
Yeah. Okay, so you evaluate the formula, like for LTL, you evaluate for the first event. For an STL formula, you evaluate it at time 0, and you evaluate the subformula on future value depending on temporal operators. So, for example, the atomic predicate x of t is greater than 0.5 will be true if we replace t by 0, then we get something that's true. Okay, so if x of 0 is greater than 0.5, then x of t greater than 0.5 is true. Is this clear? Now, eventually, 0.1.3 x of t greater than 0.5 will be true if you find any value in 0.1 in the interval 0 and 1.3, for which if you replace this t with this value, x of t greater than 0.5 will be true.
Right. It's supposed to be existing, right?
Yeah, there exists a tau, there exists some value in 0 1.3 such that x of 0's value is greater than 0.5. Okay? Then always, if you have always 0, 1.3, some subformula psi, this is true if psi is true at all time between 0 and 1.3. And psi is true at all time between 0 and 1.3. It means that we will evaluate psi on a suffix of the trace which will start at between 0 and 1.3. Okay? Any questions at this point? All right, so some visual example. Let's say you have this red signal there, and you want to say that it's never the case that the signal is above 3.5. Then you would say always x of t smaller than 3.5. And in green here, this is the region where your signal should lie in order to satisfy the formula. Okay. So the signal should be between below 3.5 in that case it is true. All right, so between 2 seconds and 6 seconds, the signal is between -2 and 2. Then, again, it's always 2 6, or globally 2 6, x, absolute value of x smaller than 2. And, okay, so you wait for 2 seconds from time 0, and this is the region where your system, your signal should be in order to satisfy the property. Okay, and maybe a more interesting property is like the stabilization property that's often used in control systems. Is whenever x is like overshoot, okay, it should settle back. It should stabilize at some region and stay in this region for some time. Okay, so always if x of t greater than 0.5, then eventually 0.06 second. Always for 5 seconds, x of t smaller than 0.5. And there should be an absolute value here. There. Okay. So in that case, now if you want to evaluate this formula, it's a little bit more complex, but on this signal, what you observe is that this goes out the region, it goes out the region again there. It means that it has to go back in this region and stays there for long enough. Okay, and then I'm done. But here I leave again my region, so I have to come back in less than 0.06 seconds, and stay there for at least 1.5 seconds. So again, this property is satisfied on this signal. Okay, questions? Yes.
The time is relative to like that condition that you enter into, because like you say you start from 0 to 1.5.
Yeah. So that's a good question. So you have an always at the top formula here. Okay. So this means that the sub-formula should be evaluated at all times. So now you should evaluate x of t greater than 0.5 implies something at all times. Okay. So you go all over there. Where is x of t greater than 0.5? Well, you have here, and then here, well, and then here, here. Okay. So now, because this is an implication, you will, from the times, it will be relative to the time where it exits this region, right? So from the time it exits the region, you should satisfy the right-hand side. So eventually 0.6 seconds, always something. Okay? And if you notice here, well, or
This is just equivalent to testing suffixes or missing.
yeah. So this always, I mean, the always operator is going to be equivalent to test the formula on all suffix of the formula, all suffix of the trace. And if you have an eventually, then it means that there exists one suffix of the formula such that the formula is true, etc. All right, so this is my overview of STL that's being used in the grader. So now a little bit about the architecture of the tool, what we did. So we organized the grading system in CyberSim around what we call, or I call, test plans. And those test plans, like I said, so this is runtime monitoring verification. So the test plans are comprised of test cases or test traces, if you wish. So there are a certain number of different traces that are obtained in specific environment settings. So you design. So this is a simple part of the system, right? That everybody can understand. So you make test cases and you test those test cases. And ideally, those test cases should cover like all situations relevant to the design requirement. So every situation that can trigger an error or something, some bad behavior, or that can, all situations where you can detect a problem with your system. And this is not an easy problem. I mean, it's easy to understand. It's not easy to design. And for each trace, for each of these test cases, then we have what we call fault monitors. fault monitors are essentially STL properties that characterize faults in the design. So we have traces, and for each trace, we have a certain number of STL properties. And each of these STL properties, if it is true, it means that an error was detected in your design. So that's the way we architected the thing. Now, this should detect any behavior that indicates some known fault. And again, this is not easy to come up with a library of known faults, of interesting, relevant faults, etc. But the first fault that we have and is that it's not satisfying the design requirements. So the default, like the default test plan that we designed have like simple test cases and a simple property that just encode what was required from you or from your design. Okay, and so, right, so the general structure of the test plan follows this idea. So you have you have declaration of signal parameters and formulas, and then you have declaration of tests. So you declare test 1, and for each test you have fault 1, fault 2, test 2 you have fault, etc. Okay, and the grader will just go through, and I think you observe this. It will just go through the different test cases, and for the different simulations. So you saw that the system was simulated for different environments, and for each of these simulations, so for each trace, you get the trace from the simulator, and for each fault, you check you monitor the STL formula, and you print some feedback depending on whether this formula is satisfied or not. Okay, and we have a small conditional, which is if the fault is critical, meaning that it's not really the fault is critical, like the feedback. If we feel that the feedback provided by this fault should be addressed right away, we just stop. We don't go over all test cases. So this is very simple logic that we plan to do there. Okay, so let's go through a complete example, and then I'll go to the real thing again. Okay, so first thing that we declare signals, parameters, and STL formulas and STL formulas. So in the syntax of this file, I'm just saying, okay, I will just use X and Y as signals for these cases. Then I define the language supports parameters. So I'm going to define like Y min and X max, which are just constant parameters. And I'm defining a sub-formula. And when designing a test, this is very important to decompose your test and your formula into sub-formula that are easily understandable. I mean, designing an STL property is not something easy. So you have really to decompose it in simple elements. So here I'm writing a very simple predicate. And this is again a formula without temporal operator, which describes a region of the state space. And I'm calling this region, I'm calling this predicate in region to live. Right. So which means that when this is true, my robot is going to be in the region that it has to live. Choose this. And this is YT smaller than Y min, or so if either YT is smaller than Y min or XT is greater than X max, then I'm in the bad region. And the top formula, which will encode the goal is missed actually, is, okay, always 020 in region to live. So basically what I'm saying here is I'm setting a goal. I'm encoding the assignment that my robot should leave a region in 20 seconds. Okay? So if this formula, always 020 in region to live, is true, it means that the robot failed. Okay? Now I'm defining the test, and in the syntax for CyberSim, what we had this syntax. We said, okay, test. We declare a test nav1, and we use environment obstacle south left. So this is one of the. If you look at the file that you have there are certain XML files, environment files, So this is one of the environment that comes with CyberSim. And I have a parameter. So this parameter in that case is the time of simulation, the simulation time. So I'm asking CyberSim to give me a simulation from 0 to 20 milliseconds. And notice that it's slightly, this is slightly longer than the horizon of my formula. My formula was always 0.20, and I'm just saying, okay, I want a trace which goes until 20.1, so that I'm sure that I can decide whether my formula is true or false, because I have all the data. Okay, I'm not interested. I'm looking from time 0 until time 20, so I'm not interested into anything that goes further. Okay. And now my fault, which is like the basic first fault, is called mist. Fault goes mist. This is named the fault, and it will use the property. It will use the property field mist that I just defined, and the feedback that I provide to the user or the student to be okay. You put on the board because it just happened that. So this is one way of encoding the generic requirement that I want to avoid this obstacle. I know that in my environment, in this environment, the robot starts at a given position with respect to the obstacle. So if it stays in the region that I define, it means that it didn't go over the obstacle. Okay, so yeah, let's start the messy part of the talk. All right, so this is our familiar environment. I have my okay. I'm using my own specially crafted solution there, which is okay. Zero. Okay, so if you remember. So what happened here, okay, is exactly it's about exactly what I just described. So I stopped it. I pressed the stop button. I didn't. So the thing read the test plans, and it loaded this special test environment where there is just my robot and just one obstacle, and my robot starts front-facing the obstacle in the left direction. And I'm saying that I should leave this region here, basically. And so my robot did that. And I got the feedback that the performance was fast and the obstacle was avoided on time. Okay? So do you have questions so far? If not, yeah, I'll continue. So now let's look at the actual test plan that was used there. So in this, this version, this release, we had the feedback mode had like 4 modes possible: debug navigation, debug hill climb, and auto-grade navigation, auto-grade hill climb. So in debug mode, the purpose was to try to provide you some useful feedback by checking as many properties as possible that could indicate a fault that you could have done. And so each of these modes correspond to one different test plan. And in the auto-grade mode, then we just remove those tests aimed at giving you feedback and just tested what the requirement for the problem. Okay, so let's move. so if you're curious, those test plans, they're located in your courseware archive or folder. You have a simulator subfolder, CyberSim subfolder, and if you go, it goes in CyberSim/data. Okay, so if you look into the subfolder data of CyberSim, then you will find those STL files, feedback nav hill, etc. So let's look at this one. If Aquamax wants, okay, so I was expecting one of my two tools to fail, but not Max. Not you. Oh, here we go. All right, so this is the test plan that was used for the feedback navigation mode. So you see, so there are quite a few properties and a few tests that we implemented, and so I'm going to go through some of them just to look at example. So this is how do you call this, domain-specific language, DSL that I implemented. Yeah.
What interprets it? What interprets this?
So this is an STL monitoring tool that I work. Yeah, this is essentially. So I have a parameter. Okay, so let's. So we have this circle fault. So I don't know how many of you bumped into this circle fault. I'm just curious.
Wait, what was this?
This is the circle fault. So this is a fault where, okay, let me show you what happens. Have this behavior. Did you see what happens here? So can anyone tell me what's happening here? Yeah. You had it? Yeah. So this is the, okay, so what we, this is our example. See if it detects it. Okay, so what we have in here in that case, what happens is the tool says first the robot cannot avoid the obstacle on time because it's dead in this region. Okay, but you saw maybe that the previous simulation it actually could go over. So the previous simulation it could go over. So the requirement, strictly speaking, was met, but clearly it's imperfect. And in that case, it didn't work at all. It didn't did it at all. And what we identified as a fault, one of the faults we identified as something that happened often is that that circle is base, and we define a formula to detect that there was a circle with this kind of behavior. And we know that the possible cause is that when you reorient the robot, you make a strict equality check for the angle where you want to go. And because it sampled the thing, it it has to do several circles before actually hitting this exact value if it doesn't work. Okay, so that's the feedback we provide. The tool can provide here. Okay, and we consider that this is a fault that should be fixed now, so it just stops the test and then say, okay, just go debug that and come back so it works. Yeah.
How many of these problems did you figure out yourself, and how many did you figure out after the move completed? Like people are saying,
So actually, we designed most of those faults before the move.
Okay.
And based on the previous iteration of this class, so a few guys last year. So we collected last year, the fall edition of this class. We collected all the built solutions of the students, and we observed this. And also, garbage Unival who worked on this too. Observe, like just the GSIs observe the different faults, and we try to make a library of those faults, encode them and yeah. So we have a couple of them. So maybe another one I can show. This one. So this one is for the hill climbing test. Okay, so the hill climbing test. Okay, what we have here. Okay, we have an environment with a height, of course, and what we have here is the robot just go there, and instead of going up, goes down. And this happens sometimes if you just reverse. If you reverse the x and y axis in the accelerometer, then this is what happens. So you would maybe check the sign of x and y. So we try to encode this. So I can go through this plan. And so this plan try to encode these different things. Okay. So for the circle, the way we did it there was we defined predicates that says whether the robot is reorienting itself or not. Right? So I'm reorienting. That is, I'm turning left or I'm turning right. Okay. And the way I do this is I'm looking at the absolute value of the left wheel speed. So, okay, basically, if the if the sum of the left wheel speed and right wheel speed is smaller than some value, which means that they have a different value, an opposite value, basically. And if real wheel speed is greater than something, I know that I'm turning right. Okay? And same thing for right. If left wheel speed is greater than something, that I know I'm turning left. Okay, so now I have two predicates which tell me, okay, I'm turning left or I'm turning right. Reorienting left or reorienting right. And then I combine those two to make like an abstract predicate that combines both of them, so that either it's left or either or right. Okay. Then I'm checking whether I'm heading in a given direction. So I'm heading 0. Okay, this is 0. And now my circle property says at some point I'm heading in this direction, and I reorient until so I do a full circle. So I reorient until I reach again this value. Do you see why it works?
Can you explain the yaw again? Why?
The yaw?
Yeah.
Okay, so yaw is the orientation of your robot. So absolute value of yaw is smaller than some angle, mean basically that you're heading direction 0. So this is your robot, and I think yaw is something like this.
So,
Okay, so
you're beginning to detect this condition
So-
only when the robot faces.
So this predicate says my robot is heading this direction.
So you're assuming if it's constantly
So
orienting.
then this predicate says I'm heading this direction, and then I'm constantly turning until I reach again this position. I never stop turning until I reach this position. This is what it does. And the circle property, now the property that will detect this behavior is going to check this at every time and see if there is any time in 0 Tmax where this is true. Okay. And okay, I can make this. I think I can make this more visual using another tool. Okay, so. So, this is a MATLAB tool where you can collect signals and verify STI properties and check STI properties, etc. So this is something I won't go into the detail of this. If you're interested, I can show more of it. But here in this interface, what I can do is that I can explore signal values, and then I can explore the satisfaction of properties. So. Here, this signal values corresponds to one recorded simulation of CyberSim sometime last year, actually. Okay, and this is one that does exhibit this circle behavior. And this you can observe. So X, Y, basically, this is the position of the robot. So if you plot, if you plot this in the X, Y axis, then you can more or less reconstruct the trajectory of your robot. Right? The robot just went there, and then it backed up, and then it zipped something there, and it went forward and then backed up. So this is basically the trajectory that the robot followed. Okay. And I don't know why it went. I think there was a wrong. No, it's not this one. I think Z is more or less constant. Okay, and so there is the orientation. Actually, there are two. We have and we have angle. Do you have an idea what the difference between and angle? Well, okay, maybe I tell you. Is actually the thing that's returned by the simulator, and angle is the simulated value of the robot. That's the
angle is the integral.
Yeah, so angle is what is measured by the robot. And is the absolute thing, the real thing that the simulator knows. But anyways, well, let's not go into this. Let's see that the same thing. So angle. So what you see here is that the angle is increasing. It is constantly increasing, right? So it's making circle. So if you look at this. Okay, so we have the angle there. Now we have the property, probably physical. Okay, we have reorient. Okay, so what I represent here, maybe I can zoom in a little bit, is the reorient property. So let's just look at the red signal. Don't pay attention to the blue thing. And the red signal is the Boolean value of this predicate. So what you can see is it's true. Yeah, it's true from this time until this time, and then the true thereafter. Okay. So. Well, if you look at reorient, this is reorient the reorient things. This is reorient left. This is reorient right. So reorient right is clearly false. So it's a 0 all the time. Okay. And so what were the other components? This was yo. Yo0 was the other predicate that I showed. And so what you can see is true at the beginning. Okay, so it's calibrated to the initial orientation. So it's true at the beginning, and it reorients until true again. At some point it's true again. At some point etc. Just making circles. So my circle property. Yeah, my circle property is there. Maybe I should put this again. Okay, so this is my circle property now. Now, how do we interpret this? So it doesn't say maybe it's a bit strange, it's not reflected here. But here, it's true here because from this point, this was true. And in this interval, the orientation, the reorient was true too. So if you look into there. Oh, okay, that's why. See? So this is true here, okay? And then you have, and then you have reorient again until it is true again. Right, so this circle property then is true there. And then the top property should be true at time 0. So if I look at phi circle, all right. So now phi circle is true. What I'm interested in is that it's true at time 0. And it's actually true even after that. I know I rejected it. Okay, so we can look at other properties. Okay, this one. Right, this one is important. I should mention that. In the slide, I said that there is no next operator in STL. So you and I knew why.
There's no order.
Yeah, this is because we have dance time, so there is no next event. So we consider that. So a next event would be. Would be something that happens in a small amount of time. So basically, the way you would encode this, it would be say eventually 0 epsilon for epsilon very small. Okay. So now, if you want to detect, if you want to encode events in STL, then it takes a little bit of thinking because there is no next. We don't have this next. So here I encoded an event bump up, meaning that, so you want to check that the bump sensor was down, and at the kind of next event, it was up. Okay? And so the way you do it is, first you define predicates, which define the state bump is up or down. So mu bump, so you have mu bump L and mu bump R. And in that case, there's also a trick with STL, which is not so nice, is that signals are all considered to have real values. We don't have type signals. We don't have Boolean signals and real signals. We have only real signals. So that a 0-1 signal is considered to be, well, it's a signal that takes value 0 or value 1. Okay. And the way you detect if it's 0 or 1, then you have to write the property bump L greater than 0.5 or greater than 50. So detect that the bump sensor in left is up, then you say bump L greater than 0.5. Then you combine. Okay, I could have made an OR here, but this works too. Now for the event bump up, then you have not. So it's at some point in time not bump up, and in 0.1 second, after 0.1 second, you get new bump is true. Okay. And this is a relatively safe way to encode. But then you have to pick carefully those parameters here, depending on the time scales of your system. Yeah. Okay, and so this is something we can, again, I think it can be useful to show there. So there, this is, all right, so this is the actual signal. Maybe I can have it more interesting.
How long is the bump signal a circuit?
Sorry?
How long is it a circuit, the bump signal?
How long is it a circuit?
Yeah.
To 0.1.
So, okay, so here,
In the simulator.
in the simulator, well, okay, so the simulator will sample, right, each time it will look at the state of the signal. And if basically the bump signal is, if you're close to the wall, it will be up. So if you stay close, as long as you stay close, I think it will stay up.
Okay.
And then if you, so here we have one case. I don't know exactly what happened in this situation, but where we have multiple bumps. There, multiple bump left.
What's the width of that? Okay.
So while here, I mean, you can look at it. There's 0.3. This is 2.5. Okay. So now if I want to check that, okay, so my bump event works well. Yeah. So here's what I get. I get a red signal. Then, so with this, what I did is I encoded a fault where I detect where the robot bump like frequently into the wall, okay, and we return something in that case saying something might be wrong because maybe you're not backing up enough, right? When you reorient, when you try to avoid the obstacle. So maybe you got this fault at some point, but I call this quick rebump. So it means that we have a bump down. It means the bump signal is down, so you just backed up. And in 0.5 second, in less than so between 0.5 second and 4 seconds after this, you again have a bump up. So basically, I'm detecting this fault. I just set this parameter to say, okay, if less than 4 seconds after my bump, I bump again, then something is wrong. Maybe not. I mean, it's not just a monitor, but this raises an alarm. Okay? Yeah. And okay, so this one is this is relatively basic. So we bump and rebump immediately. And the second one is more interesting. This one is more interesting. It says bump L then rebump R, which means you bump on one side, and after that you bump on the other side. And this can detect the fact that your algorithm maybe is not reorienting in the right direction. Right? So normally you back up, and then you move in the same direction to try to avoid the obstacle in the good direction. So you should not periodically. So I think I have one behavior. I think I have one example of this. Sorry, so this one. No, not this one. more stuff. Okay, anyway, so I think you get the all right, so now what I wanted to say is this language you can use. Like with the release that you have with CyberSim, you can write your own test plans. Okay, so if you're interested into developing some new controller for your robot, for the iRobot Create, then you can like write a controller and then write such test plan to see if it meets your design. And I think this would be a very nice project and a nice connection with the class, etc. So we do encourage you to do this. And so with the current release that you have of CyberSim, you can already do it, and we plan to make it more flexible so that you're not limited to just one robot, or you can have more interesting environments, or even maybe different simulators, not just CyberSim. This is something that we're working on now. It's not ready yet, but it will be soon, hopefully. And so the way we can do already now is that you can replace those files. The feedback nav, so now you know where this is. So this is a feedback nav file in the CyberSim data folder. So let's say instead of, if you want to write a new one, okay, you can have this. So this is the simpler one that I presented in the slides. Okay, so where I just define this region actually, and then look, I define my test and my faults. And I just replace. Okay, now I'm just going to replace that this file there. You see. So now I'm writing this into a feedback nav.scl. All right. Yes. And now, if you do this, check grid. Yeah, so you just executed the test plan. If you want to use, okay, like I said, designing STL purposes is not an easy task, so you can also use my toolbox, which is called Reach. There's a bit of a learning curve, so if you're interested in doing this, I encourage you to not wait until asking any question about it. So like what I just said, you strongly encourage to use this special design for your project if you can. And we provide support for that. And okay, do you have more questions? Yeah, there will be the I think we have like 30-minute left, and Edward, I think we have a visitor that wanted to make an announcement to the class. Sorry? I think we have a visitor that wanted to make an announcement at the end of the class.
Oh yes, that's right. This person here.
But the person doesn't seem to be there. So I think I have to hold you there for until 12:30 because somebody might come up. But there's more to you. Can certainly. I think we can look at one more examples. So this was the. Okay, so we had obstacles, outlets, wrong orientation. Right. So the requirement of the first navigation lab was that you pass the obstacle and then you keep the orientation after the obstacle. So that was I think that was relatively simple. Yeah. Yeah.
If you like, I could just show the website that you, for this thing that this person wanted to announce.
Yeah, okay, we can do this. Let me just check the. There's something interesting to say here. Okay, just no more questions?
Okay, yeah, so, we got an email asking, for permission to show, so my laptop doesn't crash, because most of the time I'm connected. No, okay, so if you have an, entrepreneurial bent, you might be interested in this, workshop, that is happening, I think, this weekend. In San Francisco. And I guess I don't really know much about it. There was supposed to be someone here to tell you about it, but there's a URL here that you can have a look at. See if I can zoom in so you can read that. Whoops. Can I display that large? I can't. That URL. Okay. So we'll consider the announcement done. Thanks.